In this video, we are going to learn about the applications of Gauss theorem. According to Gauss theorem, the net flux passing through a closed surface in free space, the net electric flux passing through a closed surface in free space is equal to 1 by epsilon 0 times the charge enclosed by the surface. 1 by epsilon 0 times the total charge enclosed by the surface. Isn't it? Is this Gauss theorem or Gauss law. The net electric flux passing through a closed surface in free space is equal to 1 by epsilon 0 times Q enclosed by the surface, and this equation can be used to find out the electric flux passing through closed surfaces. Okay. It can be used to find out electric flux passing through closed surfaces. Okay, and the closed surfaces in which the Gauss theorem is applied to find out the electric flux. The closed surfaces in which the Gauss's theorem is applied to find out the electric flux is called Gaussian surface. Gaussian surface. What are Gaussian surfaces? Gaussian surfaces are the surfaces in which we apply Gauss theorem to find out electric flux. Okay, so a Gaussian surface must be a closed surface. It can be of any shape, but it must be a closed surface. A Gaussian surface should always be closed surface, and Gauss's theorem can apply only on closed surfaces, which are called Gaussian surfaces. Okay. Now, this equation phi is equal to 1 by epsilon 0 q enclosed can be used to find out the electric flux passing through a closed surface, and this law, Gauss's law or Gaussian theorem, can also be used to find out electric field due to charge configurations. We have one more equation for electric flux. Phi is equal to, from the definition of electric flux, we have this equation for electric flux. Phi E is equal to integral E dot ds, isn't it? Integral E dot ds is electric flux, or this can also be written as integral E ds cos theta, where theta is the angle between electric field and area ds. Okay. Now we can combine these two equations. These are the two equations for electric flux. The first equation, let's name this equation as equation number 1. First equation is the equation that we get from Gauss theorem, and the second equation, this one, we can directly write from the definition. Okay. So by combining these two equations, we can write integral E ds cos theta, or integral E dot ds, integral E ds cos theta is equal to 1 by epsilon 0 q enclosed. 1 by epsilon 0 q enclosed. Integral E dot ds is equal to 1 by epsilon 0 q enclosed, and this equation can be used to find out electric field due to different charge configurations. So far we were using Coulomb's law and superposition principle to find out the electric field due to various charge configurations. For example, the electric field due to a point charge q. The field due to a point charge q at a point P, which is at a distance r from the point charge, can be found out with the help of Coulomb's law. Okay, there is no need of superposition principle here, since there is only one source charge. Superposition principle can be used to find out the electric field when there are multiple charges. Okay. So here we have only one charge, one source charge. This is the source charge here. Q is our source charge. So we can use Coulomb's law to find out the electric field at a point P. According to Coulomb's law, the force between two charges, magnitude of the force between two charges, is given by 1 by 4 pi epsilon 0 q1 q2 divided by r square, isn't it? Now, in order to find out the electric field at P, we can use the definition of electric field. It is the force experienced by a unit positive charge at a point P. So, to find out the electric field at P, we can assume that a charge of +1 coulomb is being placed at this point P. Then the electric field at a point P is equal to the force experienced by this 1 coulomb charge when it is placed at a point P. And from Coulomb's law, we can write an expression for this electric field. This electric field E is equal to force experienced by which is charge +1 coulomb charge, which is given by 1 by 4 pi epsilon 0 Q1 Q2. Q1 is the source charge Q and Q2 is the test charge +1 coulomb. So this electric field due to this point charge Q at P, which is at a distance R, is given by 1 by 4 pi epsilon 0 Q into 1, which is Q divided by R square, isn't it? So here we use Coulomb's law directly to find out the electric field due to a point charge, isn't it? Now, if we have two source charges, say plus Q, one, and another charge plus Q2, if we need to find out the electric field at a point P, we can find out the electric field at a point P by combining this Coulomb's law and superposition principle. Okay, the charge Q1 generates an electric field at a point P in this direction. Let's name this electric field as E1, and the charge Q2 also generates an electric field at a point P, which will be in this direction, in outward direction, or it points away from positive charge. So in order to find out the net field at P, we can use superposition principle, which means we can add these two fields E1 and E2 to get the resultant field at a point P. Okay. So E1 is obtained directly from Coulomb's law and E2 is obtained directly from Coulomb's law. So by combining E1 and E2, or by adding E1 and E2, for that we can make use of superposition principle. So to get the resultant field at a point P, we can add the fields E1 and E2, which is actually applying superposition principle. Okay. So in order to find out the electric field due to a charge configuration consists of multiple charges or a number of charges, we can use Coulomb's law and superposition principle. Okay. So this is the technique that we can use in the case of charge configuration which are discrete. Okay. For discrete charge configurations. For discrete charge configurations, we can find out the electric field due to each charge in this charge configuration, and to get the resultant field we can we can take the vector sum of all the fields at that point due to the individual charges. The same technique can be used to find out the electric field due to continuous charge distributions. For example, if we want to find out the electric field due to a line charge distribution, it's a continuous charge distribution, and in this distribution, this charge distribution, the charges are distributed continuously, or this charge configuration, charges are distributed continuously throughout the length of the line. Okay. And the linear charge density lambda of this charge configuration is given by Q divided by what? Q divided by length of the line L, isn't it? Now suppose we need to find out the electric field at point P due to this charge configuration. Here, since the charge configuration is a continuous charge configuration, we cannot take each and every charge in this charge configuration separately to find out the electric field at a point P, isn't it? So what we can do in this situation? We can divide the line into small sections. Okay, here we can divide the charge distribution of the line into small sections, or DL sections, say DL sections. Okay, I'm going to divide the line into small sections of length DL, of infinitesimally small length DL. Okay. Now, if lambda is the charge density of this charge configuration, the small amount of charge in this length dl, which can be taken as dq, is given by lambda into dl, isn't it? Lambda is the charge per unit length of the line, and dl is the length of the section. So the charge on this infinitesimally small section of the charge distribution is given by lambda into dl. Now we can use Coulomb's law to find out the electric field at a point P due to this small section of charge dq. Okay. For that, we can assume that a point charge, 1 coulomb, is placed at this point P, and according to Coulomb's law, we get the electric field due to this small section dE. Now we can call that electric field as dE. This is the electric field due to a small section dq of the charge configuration. It is given by 1 by 4 pi epsilon 0 the charge dq divided by, if r is the distance towards the point P from the section dl, dq divided by r square, or this can also be written as in terms of charge density. dE is equal to 1 by 4 pi epsilon 0 lambda dl divided by r square. This is the electric field at a point P due to this small infinitesimally small section dl of the charge configuration. Now to get the net electric field at a point P, we have to divide this, or we have to assume that we are dividing this entire section into small sections of dl each, infinitesimally small sections, and then find out the electric field at a point P due to all these sections, and then add the electric fields due to these small sections to get the net electric field at a point P. And when we do this for a continuous charge configuration, this mathematical technique is actually integration. This is not summation. For continuous distributions, we can use the technique of mathematical technique, which mathematical technique? Integration, to find out the net electric field at P. Okay, so the net electric field at PE, let's take that as E. It is given by integral 1 by 4 pi epsilon 0 lambda dl divided by r square. Okay, integral 1 by 4 pi epsilon 0 lambda dl divided by r square. The same we can do for a surface charge distribution also. If we have a surface charge distribution of charge density sigma, where sigma is equal to charge divided by area. Okay. So in order to find out the electric field at P, we can divide the entire area into small sections, small area sections of dA. Okay. Then at point P, the electric field due to the small section dA, the charge on this section is given by dq. dq is equal to sigma into dA. If sigma is the charge density, it is a charge per unit area, the charge on this given area dA, it is equal to, or the charge on the infinitesimally small area dA, it's equal to sigma into dA. So the electric field at a point P due to that infinitesimally small section dA can be written as 1 by 4 pi epsilon 0 sigma dA. Okay, dq divided by r square, or sigma dA divided by r square. So in order to get the net field at P, we can integrate this dE, that is for integral 1 by 4 pi epsilon 0 sigma dA divided by r square. Okay. And for volume charge distribution also we can use, here also we use the Coulomb's law and superposition principle to find out the electric field. Okay. Now for a volume charge distribution also we can use the same technique, and here we have to divide the entire charge configuration into small volumes. Okay, small volumes, infinitesimally small volumes. Let's take this is an infinitesimally small volume section. Let's name this as dV. Okay. And the volume charge density rho, it is given by Q divided by V, isn't it? So the charge enclosed by this small volume dV can be taken as dQ, which is equal to rho into dV. Okay. Where rho is the charge per unit volume. So the charge in this infinitesimally small section dV is rho dV. Hence the electric field due to this infinitesimally small section dV can be written as, at a point P, which is at a distance r, the electric field due to this infinitesimally small section can be written as 1 by 4 pi epsilon 0 rho dV divided by r square, and the net electric field at the point P due to the entire charge configuration can be written as integral 1 by 4 pi epsilon 0 rho dV divided by r square. Okay. So for a continuous charge configuration also, we can use Coulomb's law and superposition principle to find out the electric field. Okay. If it is a discrete charge configuration, we can take each and every charge separately, then find out the electric field at the given point due to these individual charges, and then take the vector sum to find out the net field at the given point. And if it is a continuous charge distribution, if it is a linear charge distribution or volume charge distribution or surface charge distribution, we can use the same principle, superposition principle and Coulomb's law to get the electric field. But instead of summation, we have to do the integration. So if linear charge distribution is given, we can use this equation 1 by 4 pi epsilon 0 lambda dl divided by r square. And for surface charge distribution, integral 1 by 4 pi epsilon 0 sigma dA divided by r square. And for volume charge distribution, integral 1 by 4 pi epsilon 0 rho dV divided by r square. And I have written all these three equations in its scalar form only, and if we need to write it in vector form, we have to multiply these magnitudes with a unit vector. Okay, I'm not going to do it here. So these three equations are based on Coulomb's law and superposition principle. Okay, Coulomb's law and superposition principle. So this is a method or technique that we can use to find out the electric field due to any charge configurations, even if it is a discrete charge configuration or a continuous charge configuration. But in most of the cases, using this technique is not easy. Okay, mathematics is a little bit difficult, especially for continuous charge configurations, since the mathematics that we have to use is integration. This is a little bit difficult, or it is difficult to use this technique. In most of the cases, this technique is difficult to find out the electric field due to charge configurations. If we have more than 3 or 4 charges, it is difficult to find out the electric field due to the charge configuration by adding the field due to individual charges here, since we have to do the vector addition. Okay. So even though we can use the this particular technique, which one Coulomb's law and superposition principle, to find out the electric field due to any charge configurations, it is not always easy to do so. Okay. So in some situations, we can use Gauss theorem to find out the electric field due to charge configuration, especially electric field due to continuous charge configurations. Okay. Now we have two techniques to find out the electric field due to charge configurations. One is by using Coulomb's law and superposition principle. Coulomb's law and superposition principle. Okay, Coulomb's law and superposition principle. Superposition principle. Okay. And the second technique is by applying Gauss theorem. Okay, by applying Gauss theorem. So when we apply Gauss theorem, we can use this equation, integral EDS cos theta is equal to 1 by epsilon 0 q enclosed to find out the electric field. Okay. So these two techniques, both Coulomb's law and superposition principle and Gauss law, can be used to find out the electric field due to any charge configurations. Yeah, both can be applied for any charge configuration, but in some situations it will be easy to use Coulomb's law and superposition principle. For example, if we want to find out the electric field due to a single positive charge or negative charge or point charge, or due to a system of two charges, or a system of two equal and opposite charges like that of a dipole, Okay, in these cases, it is easy to find, easy to use Coulomb's law and superposition principle. And in some situations, applying Gauss theorem is easier than Coulomb's law and superposition principle. Okay, so in this section, we are going to apply Gauss theorem to find out the electric field due to a few charge configurations in which it is easier to find out the electric field. Okay, so that is what we are going to do in our next sections. Now let's check how to use or how to apply Gauss theorem or Gauss law to find out the electric field due to charge configurations. For that, let's consider a charge configuration. Here I'm going to take a continuous charge distribution. And if we need to find out the electric field at a point P near this charge configuration, first we need to imagine or consider a closed surface. A closed surface, a suitable closed surface, a suitable closed surface which passes through the point P. Okay, so this is the first step. So these are the steps that we need to follow while using Gauss theorem to find out the electric field due to charge configuration. First step is to select a suitable closed surface which passes through point P. Okay. Now the second step is to find out the left hand side of this equation, equation number 1. Okay, so the second step is to find out the left hand side of this equation, which is integral E ds cos theta. Okay. So while choosing a suitable closed surface to apply Gauss theorem, the surfaces which are used to apply Gauss theorem are called Gaussian surface, isn't it? Gaussian surface. So the first step is to select a suitable Gaussian surface. So while choosing this suitable Gaussian surface to apply Gauss theorem, we need to consider a few points. First one, it is better. It is not a must condition actually. It is better in order to make the mathematics easy. It is better to select a surface. It is better to select a surface on which at every point the value of cos theta, okay, the value of cos theta is either +1 or -1 or 0. It is better or convenient to select such a surface. What type of surface? The surface on which at every point the angle between electric field and area vector, okay, is such that cos theta will be equal to +1 or -1 or 0. For example, let's consider a surface here. If this is the closed Gaussian surface or closed surface on which we are going to apply Gauss theorem, and when we consider an area vector ds to apply Gauss theorem or to find out this integral E ds cos theta, first we need to consider small area ds, and this is the area vector of the small area ds, which is in outward normal direction, or at every point on this surface, the surface ds. The electric field, if the electric field is in the same direction of the area vector ds, theta is equal to, or theta will be equal to 0, and cos theta will be equal to +1. Okay, and if the electric field is in the opposite direction of area vector, the angle will be equal to 180 degree, and cos theta will be equal to -1. Okay. And if we consider an area vector ds or small area ds, when we consider small area ds, so area vector is in outward normal direction. If the electric field at this point due to this charge configuration is perpendicular to the area vector, the angle between these two will be equal to 90 degree, and then cos theta will be equal to 0, isn't it? So it is better to select or to choose such a surface so that at every point on the surface, the value of cos theta uh, will be equal to +1 or -1 or 0. Yes, so what is the advantage of selecting such a surface? If we select such a surface, the term cos theta will not be there in the integral. Otherwise, we need to integrate this cos theta term also. So the integration will be more easier. Yeah. So this is the first point that we have to remember when we select the Gaussian surface. Now the second point that we need to consider is at every point on the surface which we select, closed surface or Gaussian surface, which we select to apply Gauss theorem, the magnitude of the electric field, the magnitude of the field will be the same at every point. Okay, the magnitude of the electric field, if it is same at every point, we can take the term E outside the integral, isn't it? If the magnitude of electric field, if it is same at every point on the surface, Gaussian surface, we can take, while integrating, we can take the term E outside the integral and we can write the term like this, integral E ds. It will be either equal to plus in E integral ds or minus E integral ds or 0. Okay, so if we take the electric field outside the integral, the integration will be very easy. Okay. Now we need to know only this integral ds, which is the entire surface area of the surface which is selected to apply Gauss theorem. Okay. So this integral ds here, it is the surface area of the Gaussian surface. Surface area of the Gaussian surface. Yeah, so these are the first two steps. First, select a suitable surface. Suitable means what? When we select a suitable closed surface, we need to consider these things. Which all things? Select a surface on which at every point the value of cos theta is either +1 or -1 or 0. Yeah, or theta is either 0 or 180 or 90 degree. Then select a surface on which at every point the magnitude of the electric field is the same. Yeah. Then the integral will be like this in this form, E into integral ds, where integral ds is the surface area of the entire Gaussian surface. If we select a spherical Gaussian surface, this integral ds will be equal to 4 pi r square, and if we select a cylindrical Gaussian surface, it will be equal to pi r square if the surface is flat surface, and if it is the curved or cylindrical surface, it will be equal to 2 pi r into L. Okay, if we select a cubical Gaussian surface, it will be equal to a square, and so clear. Now the third step is to find out the right hand side of this equation, 1 by epsilon 0 q enclosed. If we know the charge enclosed by the surface, the Gaussian surface, we can find out this right hand side 1 by epsilon 0 q enclosed, and after finding out this right hand side, we can equate these two, 2 and 3, steps 2 and 3, which will be equal to E into integral ds equals 1 by epsilon 0 q enclosed, and we can use this equation to find out what the electric field due to the charge configuration. Now we know the steps to be followed to find out the electric field due to charge configuration by applying Gauss theorem, isn't it? So the first step is to select a suitable Gaussian surface. And we did see what all things we need to consider while selecting such a suitable Gaussian surface to make the mathematics, especially the integration step, easier. Okay. Now, certain charge configurations, the electric field due to certain charge configurations have some kind of symmetry. There are charge configurations with some kind of symmetry. If we know the symmetry of a charge configuration, it will be easier to select the Gaussian surface to apply Gauss theorem. For example, The electric field due to a point charge. Electric field due to a point charge. Okay, electric field due to a point charge has spherical symmetry. It has spherical symmetry. The electric field due to a point charge has spherical symmetry. Let's check what does it mean. Now let's consider a point charge. This is the source charge, the charge which generates the electric field. So if we consider a spherical surface, with the source charge plus q at center, plus q or minus q, the source charge is a point charge here. So if we consider a spherical surface with the charge at the center, at every point on the surface of the sphere, the magnitude of electric field will be the same. Okay. So if this spherical surface is a surface of radius capital R with the plus q charge at the center, the electric field at a point P1, the magnitude of the electric field at a point P1 is given by 1 by 4 pi epsilon 0 q divided by the distance square. Distance here it is r square. Now if we consider another point P2 on the surface, the magnitude of the electric field at this point P2, this is also equal to 1 by 4 pi epsilon 0 q divided by r square, since the distance is the same. So if we consider another point P3, here also the magnitude of the field will be the same, 1 by 4 pi epsilon 0 q by r square. Okay, so at every point on the surface, the magnitude of the field is the same. Hence, we can say that the field has a spherical symmetry. And if the electric field due to a certain charge configuration has a spherical symmetry, we can select a spherical Gaussian surface. Okay, we can select a spherical Gaussian surface, to make the mathematics simple. Okay, so that is the advantage of knowing the symmetry of a charge configuration. A point charge has spherical symmetry. So if we need to find out the electric field due to a point charge at any point, we can select a spherical Gaussian surface with the charge at the center, which passes through the given point to apply Gauss theorem, which makes the mathematics simple. Clear. And another charge configuration which has symmetry is a uniformly charged infinite line, straight line. Okay. The charges are distributed uniformly throughout the length of a straight line which has infinite length. Okay, so this is a uniformly charged straight line of infinite length, or straight wire of infinite length. Such a charge distribution has cylindrical symmetry. Yeah, this charge configuration has a cylindrical symmetry. So if we use a cylindrical Gaussian surface, if we need to find out the electric field at a point P near this charge configuration, we can select a cylindrical Gaussian surface with a radius r, where r is the distance towards the point from the charge configuration. The mathematics becomes simple or easy. Okay. So if a charge configuration has spherical symmetry, we can select a spherical Gaussian surface to make the mathematics simple. And if a charge configuration has a cylindrical symmetry, we can choose a cylindrical Gaussian surface. Here the cylindrical Gaussian surface has radius r, and the charge distribution is the axis of symmetry. It is the axis of symmetry. Okay. So this case we will discuss in detail later. So Now you just need to remember this point. This particular charge configuration, which one? A uniformly charged straight wire of infinite length has a cylindrical symmetry. So if we select a cylindrical Gaussian surface to find out the electric field due to this charge configuration, we can make the mathematics simple. Okay. Now another one, a uniformly charged a spherical shell. Okay, uniformly charged spherical shell. Uniformly charged spherical shell. Okay, it is a spherical shell, and the surface of the shell, it is charged uniformly. Yeah, it's also a surface charge distribution, and this charge distribution also has spherical symmetry. It has a spherical symmetry. Okay, so we can select a spherical Gaussian surface outside the spherical charge distribution. It has a spherical symmetry. So if we need to find out the electric field at a point outside this this spherical charge distribution, we can select a spherical Gaussian surface to find out the electric field. And here again, selecting spherical Gaussian surface makes the mathematics simple. Okay, so Gaussian law or Gauss law is useful towards a much easier calculation of the electrostatic field when the system has a some kind of a symmetry. Okay, so if the system has some kind of symmetry, and if we know the symmetry of the system or the charge configuration, electric field due to the charge configuration, we can select a suitable Gaussian surface to make the calculation simple. We are going to select some such charge configuration which has symmetry, and we will apply Gauss theorem to find out the electric field due to these charge configurations. So before we move on to our next section, in which we apply Gauss theorem to find out the electric field due to certain charge configurations, let's first go through some important points regarding this law, which law, Gauss law or Gauss theorem. Okay. So this is the first point. Gauss law is true for any closed surface. The surface must be closed. It is true for any closed surface, no matter what its shape or size. Okay. But we did see that it is convenient to select the Gaussian surfaces by considering the symmetry to make the mathematics simple, isn't it? Okay. If we can do the integration, we can select any Gaussian surface of any shape or size. Only one condition is there, which is the condition the surface must be a closed surface. Okay, but it will be easier. The mathematics will be easier if we select a Gaussian surface by considering the symmetry of the charge configuration. Okay. So Gauss law is true for any closed surface, no matter what its shape or size. Now, the term Q on the right hand side of the Gauss law includes the sum of all charges enclosed by the surface. The charge may be located anywhere inside the surface. Okay. So according to Gauss theorem, phi is equal to 1 by epsilon 0 Q enclosed. So this charge Q on the right hand side, the charge Q on the right hand side of this equation includes the sum of all the charges enclosed by the surface. The charges enclosed by the surface. We can consider only those charges which are enclosed by the surface. The charges may be located anywhere inside the surface. In the situation when the surface is so chosen that there are some charges inside and some charges outside, the electric field whose flux appears on the left side is due to all the charges, both inside and outside. But the term Q on the right side, however, represents only the total charges inside. Okay. So now suppose consider a situation in which there are some charges inside the Gaussian surface and some charges outside the Gaussian surface. Okay. In this situation, the flux passing through the surface, the net flux passing through the surface, that means the term in the left hand side of the equation, this one, it is the net flux passing through the surface. This is due to the charges both inside and outside the surface. The flux is due to the charges both inside and outside the surface, but the charge term in the right hand side of the equation, Q enclosed, represents only the charges which are inside. Okay, so this point you just have to remember. In this equation, the left hand side, phi E, which is the flux passing through this surface, and the stem in the left hand side is due to the entire charge configuration, which means the charges in both the net charges inside and the net charges outside contribute to the stem phi E, but the charge stem in the right hand side is only right hand side represents only the total charges inside the surface. Okay. Now the surface that we choose for the application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charges. Okay. So when we take a Gaussian surface to apply Gauss theorem, we must take care not to let the Gaussian surface pass through any discrete charges. There cannot be any discrete charges on the surface. Can be there inside or outside, but no discrete charges should be there on the surface. Okay, there should not be any discrete charges on the surface, or we must take care not to let the Gaussian surface pass through any discrete charges. It is because the electric field due to a system of discrete charges is not well defined at the location of any charge. Okay. The electric field due to a system of discrete charges. We know that, for example, if we consider point charge Q, we know that at a distance r from the charge at a point P, the electric field is 1 by 4 pi epsilon 0 Q divided by r square. But at origin means that at the point where the charge is located, where the source charge is located, the magnitude and the electric field strength is not well defined. Okay, it is not defined. The field is not defined. It is not defined at the point where the source charge is located. At the point where the source charge is located, R will be equal to 0, isn't it? R will be equal to 0, and at this point where R is equal to 0, the electric field is not well defined. So when we choose a Gaussian surface, we must take care not to let it pass through any discrete charges, but the Gaussian surface can pass through a continuous charge distribution. The Gaussian surface can pass through a continuous charge distribution. When we have, if we have a continuous charge distribution, if the charge distribution is continuous, and if we consider a Gaussian surface like this, it is possible, since the Gaussian surface can pass through continuous charge distribution, but there must not be any discrete charges through which the Gaussian surface pass. Gauss law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This point we already discussed, and this is facilitated by the choice of a suitable Gaussian surface. If we know the symmetry of the charge configuration, we can easily select a Gaussian surface to make the calculation simple. Okay, so finally, Gauss law is based on inverse square dependence on distance contained in the Coulomb's law. Okay, so or Gauss law is a direct consequence of Coulomb's law. Okay, Gauss law is a direct consequence of Coulomb's law. So any violation of Gauss law will indicate the departure from the inverse square law. Any violation of Gauss law indicates the violation or the failure of Coulomb's law. So these are a few points given in NCERT textbook. You just have to remember this.